theme for this conference is Changing Chemistry in a Changing World, so I thought I would talk about the interaction of changes in climate and chemistry in the eastern United States, where I come from. And even though it's a slightly personally embarrassing story that I'm about to tell, this is a diagram. This is what the eastern part of Maryland looks like. It's kind of an estuary. That's a coal-fired power plant. That's a NASA P-3 research aircraft, and I'll talk about some of the results from Discover-AQ. But before that, the real point is, what's the response of our most important pollutant, that is ozone, to changes in climate? The most important climate factor for ozone appears to be temperature, and the increase in both the duration of the ozone season and the number of heat waves can have an impact on air quality. This is one of the few easily directly attributable causes of morbidity and mortality, therefore loss of money, if you're talking to politicians, that you can pin on climate change. So it's a useful thing to study. So I'll talk about what's called the climate penalty factor. We heard from Dr. Porter a little bit about that yesterday. And the eastern U.S., being mid-latitudes, has experienced more or less the global change in temperature of about 1 degree and a slight shift in precipitation away from the annual average about the same, but a little bit away from the summer to the fall. So there is a climate penalty factor. Models have long predicted it. There's a nice review. So, but what, if anything, can we do about it? Okay, here's a diagram similar to what you saw yesterday. The units on the x-axis, for those of you who didn't grow up in the United States or the Sultanate of Brunei, are degrees Fahrenheit, and that's because this diagram was put together to talk to policymakers. So you have to speak very slowly, use words of 1 syllable or less, and talk to them in the units that they're used to. It's very important. What do we see here? There is a temperature dependence of ozone, and it's messy. It's hard to pick out exactly what's going on there. It doesn't appear to be linear. So I had a very clever student, Brian Bloomer, who, oh, that's the standard, by the way, for 1 hour, 8-hour standards. Yeah, oh, Baltimore and Washington violate EPA standards for clean air. Okay, Brian Bloomer is very clever with statistics, and he did these location statistics. So I'll explain what this is. For any given temperature bin, he looked at the median, the quartiles, and the 95th and 5th percentile for rural sites in the eastern United States, at the whole eastern United States. I'm just going to focus on the mid-Atlantic area right now, but the results are similar elsewhere. So the definition of the climate penalty factor is the slope of this line. Good. So these are observations, a snippet of observations from the mid-Atlantic. These are prior to 2003, and you can see that pretty much a linear relationship between temperature and the highs here, the medians and the lows in rural areas. Urban areas have a slightly different relationship because you can get funny stuff for the minima of ozone by titration. Anyway, this is everything we saw prior to including 2002. Well, after a big fight with a lot of power companies and a lot of bureaucracy in the eastern United States, we managed to institute what's called the NOx-SIP call. Don't worry what the acronym stands for, but it basically means the power plants were forced to install scrubbers, and they made a substantial reduction in the NOx emissions. And this is what happened to the ozone concentrations and the temperature dependence after the NOx-SIP call. So we went from about 3.3 parts per billion of ozone per Kelvin to 2.1. So we go back and forth. So a big improvement. So yes, there's a climate penalty factor, not just in models, but in the observations as well. And it does appear to respond, as somebody asked, Hunwat asked yesterday, well, what's the impact of chemistry on the climate penalty factor? So it's there. And a degree is under human control. Now, One of my students, Herb, asked me, okay, why does ozone respond to temperature? And I gave him all the classic answers. There's pan dissociation at high temperature. I think Hunwatt had something to do with that idea. When it's hot, it's sunny, it's stagnant. And he said, well, you know, the NOx emissions are higher on hot days. And I said, say what? It didn't occur to me. But he looked at the data, and he saw these are OMI NOx observations, OMI the NASA Dutch-Finnish satellite, as a function of temperature. And certainly for these first few years, you see a positive correlation. We looked at the direct emissions too. And so, well, emissions are higher on hot days because we use more electricity for air conditioning. Uh-oh, that might have an impact. So we see, at least for a while, this, by the way, this is the general trend in NO2, so we have been winning the battle to control the important ozone precursors, and very crudely, the ozone has been coming down. That's not quantitative, but that's just descriptive. So what's the impact of these changing emissions on the climate penalty factor? So what's the relationship between ozone and temperature? And to answer that question, we tease apart the relationship. We have this representation of the increase in emissions as a function of temperature. That's provided to us by the EPA. And Patty Castellanos helped us analyze and make sense of the ambient NOx concentrations. They're a function of the emissions. And then there's the ozone production efficiency that we can get from direct observations. Ozone production efficiency is defined as the number of ozones you get per NOx molecule that you oxidize away, that you consume. So we use some Discover AQ data, direct observations, to get the ozone OPE, ozone production efficiency. We put it all together, and you can get the fraction of the climate penalty responsible that we can attribute to emissions, temperature-dependent emissions from power plants. So this is a plot of the emissions and the daily temperature for different time periods here. You can see the general trend earlier to later. There's always an increase in emissions with increased temperature, and this is the slope for the summer in tons per degree. It's come down over the years, but it's still there. So this relationship was investigated by Herb, and a couple of papers have appeared in the reviewed literature. So this is a plot of the surface NOx concentrations as a function of emissions, and indeed we can relate the surface NOx to the actual emissions, and that makes sense. You would then expect the ozone to respond not to the emissions but the actual concentrations. So this is the these are the climate penalty factors that we got from the observations. So the bottom line for this part is that prior to 2002 we could explain possibly the majority of the climate penalty factor in terms of NOx emissions increasing on hot days. That's come down in time. All right, well, there's more to generating ozone than just NOx. These are formaldehyde observations from OMI as a function, the summer averages for the past few years, and temperatures plotted on there as well. So you can see, you can see that there's a pretty good correlation between temperature and formaldehyde. Why is that? The main source of formaldehyde, even in the fairly industrial, heavily populated eastern United States, is trees. Isoprene oxidation, at least in a NOx-rich environment, leads to formaldehyde. And so the most important and hydrocarbon in terms of reactivity for making ozone is absolutely isoprene in our part of the world. And so we can, and isoprene comes out of trees faster when it's warm. There are very complicated models for predicting isoprene emissions. They have relationships with temperature and soil moisture and photosynthetically active radiation and so on, but temperature is always the most important. Precipitation is shown on here with formaldehyde, and there is possibly some correlation. There is some influence that we think we can explain. So here is just a sort of a simple correlation coefficient plot, scatter plot of OMI's formaldehyde versus temperature. Brian Duncan's done some of this stuff before, and The correlation is really pretty good, and there's one particularly dry year. You take that out, the correlation goes from good to excellent. So temperature is most of what's going on. We have pretty reliable rain, but I'll show you some nice pictures now. I'm running out of time. Here we go, if I'm lucky. There, this is just, you have to have nice graphics, so how her put these together. This is the column content formaldehyde as a function of time for the summer, just for July, sorry, for the past few years. Okay? So you can see that there's quite a bit of interannual variability depending on the weather. So I'll walk through them a little more slowly now. This, the top left is temperature. The bottom right is formaldehyde. So we have, it's almost always hot in July, but not always, and sometimes it's dry, so we'll walk through this. So there's 2005, 6, hot year, lots of formaldehyde. So a cooler year, less, 2008. So this was a particularly dry July in 2009, and the trees responded to that. So 10, 11, 12, and 13 was a very dry summer, so we saw much less formaldehyde. So this is interesting. There is some relationship between the weather, the biosphere, the chemistry in the atmosphere, and the habitability of the eastern United States. Oh, for the sake of orientation, I live about here. Washington, D.C. there is, Baltimore's there, and New York's up here. All right. So what are the take-home messages? If the eastern U.S. is anything to indicate, that you can expect, indeed, you will get somewhere between 1 and 3 parts per billion of ozone increase for every degree Celsius. That turns out to be a rather expensive problem, because just in the eastern U.S., the cost of reducing NOx to control ozone is estimated at that's not a typo, $1 billion per part per billion of ozone to control NOx emissions. And it's worth it in terms of morbidity and mortality, in terms of the lives you save, and the emergency room visits avoided, and so on. There is an interesting relationship. Some of this is natural, biogenic feedbacks and stuff, but some of it is under human control. We can control our fate in terms of the climate penalty factor and in terms of our environment. But it's expensive, and it's a real cost. People want to know, well, why do we care about a warming planet? Well, if you have a part per billion per Kelvin and $1 billion per part per billion, you do the math. All right. So there's some good news in that the NOx controls have been effective and ozone is coming down. The bad news is that if we lose the political will, these NOx emissions can creep back up again, and there's some evidence that they have lately. So we must remain vigilant. With that, I will say obrigado and finish.
Thanks, Russ. Okay, we've got Alex right here. Right here. Yeah. Alex.
It's too shy.
Yeah, really nice talk. I just had a question about the OPE that you said you used from Discover-AQ measurements. Does that not depend on the chemical environment? So there's no constant OPE. It's going to change as the NOx emissions change.
Indeed. Oh yeah, you were paying attention. I glossed over that because I've only got 15 minutes total. Yeah, sure. We used a range of values. It was between 2 and 8. I should have said that. Depending on, there it is. Actually, it turns out that for the Discover-AQ data, which were focused right on the urban areas of Baltimore and Washington, there was not a terribly strong dependence of the ozone production efficiency on the NOx concentration. But absolutely in the literature, there is, and one must be careful. So there are always little twiddles in front of my 2/3, 1/3 fraction that you can attribute, and most of the uncertainty comes from the difficult to quantify concept of ozone production efficiency. So yeah, great question. Thanks for reminding me. I forgot to say that.
Mark Lawrence?
So I'm curious about your billion per year, or no, your billion per PPP. Is that per year, or is that
Yes.
a one-time investment?
No.
That's a per-year investment.
That's continued. That includes the initial cost plus the operation expense. The problem is to run selective catalytic NOx reduction, SCRs, is expensive. And so the power companies don't like to do it. If they don't have to, they don't. This is a huge political battle right now. I mean, they've invested billions to put in the equipment. They can save millions by not running it.
And this
so
is
we're
only
trying-
US-wide, or is this, and how does it split between private sector and what the government would have to put in through taxpayer?
It's for the eastern U.S. Utilities in the eastern U.S. are a kind of complicated, as you remember, back from when you were an American, complicated mixture of public and private. So I can't tell you what fraction's paid for by public and what fraction by private.
Okay,
It's a
thanks.
good question.